Hi, my name is Omar Al-Samari, and my team members are Luigi Santiago and Arian Singh. This is our project, the 32-bit MIPS processor with 5-stage pipelining and model sim. Today, we'll be discussing the project goal, basic MIPS background, the main modules needed for the processor, a custom wiring schematic display, and also a program demonstration. First, the project goal. The project goal is to implement a 32-bit processor with 5-stage pipelining that will be able to execute a program created off the MIPS instruction set architecture. The instructions that the processor will be able to execute are arithmetic and logic instructions such as AND, OR, NOR, add, subtract, set less than, add immediate, multiply, and divide. The processor will also have data movement functionality such as load word, store word, move from high, and move from low. Flow control will also be included into the processor, and those instructions are branch if equal and jump. A hazard detection unit and a forwarding unit will also be included to support forwarding values and stalling the processor. Now we'll go into the basic background about MIPS. So the MIPS architecture has a register file that contains 32 32-bit register values, and the 0th register of the register module always contains the value of 0. The instruction memory has a data width of 8 bits, and the instructions are a fixed 32-bit instruction width. The 5 pipelining stages are instruction fetch, instruction decode, execute, memory access, and write back. And the purpose of the pipelining stages are to increase the throughput of the instructions. Now, here are the simple MIPS instruction formats for 3 different types of instructions. The R type, so register type of instructions, I type, immediate type of instructions, and J are the jump type of instructions. For each instruction, the upper 6 bits of the format is the opcode for the specific instruction. So now we'll talk about the main modules needed for the processor. The instruction memory is needed, the data memory module, arithmetic logic unit, also known as the ALU, which will be used to execute a lot of the instructions, the forwarding unit, which is used to forward values that have been recently calculated and not stored into the register module yet, a hazard detection unit, which inserts bubbles or stalls into the processor when other instructions are utilizing the units, a main control module, and of course the 4 pipeline register modules, which will go in between every pipeline stage. So the first one will be the instruction fetch, instruction decode, pipeline register module, instruction decode, execute module, register module, execute memory module, and then the memory write back module. And then we use the multiple muxes of various sizes for this module, for the processor as well. So now we'll have a wiring schematic display. So we had a lot of trouble with the processor, and we did not have a one block diagram that depicted all the units used for the processor online. So we created our own wiring schematic, and all data bus are defined in the wiring schematic, and all muxes are also defined. All wire numbers that were used in the model sim implementation were also drawn onto the schematic, so it'll be easy to troubleshoot. So now I will show the wiring schematic the wiring schematic that we created. So we drew along one note, and as you can see here, all the modules are included, and the wires used to connect between the modules were depicted here. So there's a wire 1 connects to the program counter, which also connects to the instruction memory module, which also connects to this adder up here. And we can also see that each wire has a data width defined. So 32 bits, 32 bits, 32 bits. And then if it's not depicted, it's 1 bit. So here is the instruction fetch stage. And then this is the register module that was created to have the values pass through from one side to the other. Instruction decode stage, and more, and the modules here that are kind of important are like the main control unit, the register module, and then as you see here, there's a mux of different size used here, comparator and AND gate, and then these highlights here are used to reference an output. So for example, this L16 output of the AND gate connects to the input of this mux. But we didn't it's not it'll be unnecessary to draw a line, so we just use the same color highlighter to depict it. And as I said again, this schematic, it was used to find any issues in our model sim implementation and really help have everything running smoothly and helped with troubleshooting. So this is the execute module, execute execution stage. There's the ALU, the forwarding unit. The hazard unit is here in the instruction decode stage. Forwarding unit, multitude of muxes. Here's the memory access stage, which has the data memory module. And last, the write back stage. Going back. Now we'll have a program demonstration. So here's a live program demonstration. So this is the test bench. So here to the left are all the modules created for this mod. And then here's the top level module, which has all the wires used and all the modules instantiated here. And here's a test bench module. Test bench module, which instantiates the top level module. And we did a time scale of 1 nanoseconds per 100 picoseconds, and the clock changes every 10 nanoseconds. The clock changes every 10 nanoseconds, so it gives us a period of 20 nanoseconds, which is a 50 megahertz clock. So here in the instruction memory module, a lot of instruction, I've already commented all the instructions to test them, of course, and now we'll execute some of these instructions. So the first instruction we will execute is a add instruction, an arithmetic. So here, register 1 will have the sum of register 7 plus register 8. So that's the first instruction, and we'll go to the register module. So register 7 and 8 will be initialized both with the value of 2. So register 1 should then have the value of 4 after the instruction executes. So let's compile, let's start the simulation. So now we'll go to the memory list and open the register file. So the first instruction takes 5 periods, and after that, 1 period is needed to execute every instruction, since this processor does have pipelining. So after the first period, register 7 and 8 are initialized with the value of 2. And then after 4 more executions, so 2, 3, 4, 5, register 1 has the value of 4. So that demonstrates an add instruction. Next instruction we will show is we'll show an multiply and also data movement, which will be move from low and move from high. Nope. So we'll take off this one. So these are the three instructions for this program, mini program here. So multiply register 7 and 8, and the value will be stored, but nothing will be done with the value until we use these two instructions, move from low and move from high. Register 7 and 8 will be initialized with the value of 5 and 2. So 5 times 2 is 10. After move from low executes, register 1 should have the value of 10. And then since the rest of the 6 equal 4-bit value calculated is 0, are 0, so move from high, register 2 should have the value of 2. So now execute that instruction. Simulation. So again, here, go into the memory list. So after the first period, register 7 has the value of 5, and register 8 has the value of 2. After 4 more periods, 2, 3, 4, 5, the multiply instruction has executed. So now after another period, move from low should execute, which will have register 1, I believe, will have the value of 10. That depicts right there. And then now move from high will execute, which will give the register value 2 of 0. All 0. So as we see there, the multiply instruction was demonstrated, and also move from high and move from low instructions were demonstrated. So let's quit this. Now the next instruction, I want to show is using the data memory module. So take out this, and then I did not want to make this video too long, but all these instructions here are used and worked. All these instructions are here. So now we're going to use a store word instruction. And we'll open the data memory module. And here, perfect. So data memory has the value. So the first 0th mem file position of the 0th position of the memory file is initialized with the value of 0. Here, then go to store word. In the register file, register 8 is stored with the value of 10, and register 0 is also stored with the value of 0. So this instruction here, store word, takes the value from register 8 in the register module, in the register module, which is 10, and it will store into base address 0, register 0, plus the offset is 0, which is the 0th place in the memory file. So after 4 periods, we should have the value of 10 in the data memory module here, because the 4th pipelining stage is the memory access, and that's when the value should be stored. So here we're going to compile the modules I edited. And let's simulate. Now we're going to open up the register file and the memory file. So after the first period in the memory file, the first place in the memory file is initialized as 0, and the register file register 0 has the value of 0, and register register 8 has the value of 10. So now after 3 more periods, the value of 10 should be stored in the register file. Here, so after 4 periods, register the 0th memory address 0 in the mem file has the value of 10. So that demonstrates the memory file and the store word instruction. And then just to clear up any confusion with the store word instruction, the address in register 0, which is 0, is taken, and then offset of 0 is applied to that base address. Since they're both 0, 0 plus 0, 0, and that means the 0th place in the mem file is written to. So now I guess we'll comment this out. So now the last demonstration I would like to do is to test the branch if equal instruction and also the forwarding unit. So this is a mini programmer created here, which consists of 5 total instructions. And then this is the instruction itself and placed in the memory file. The first instruction adds the register values of 2 and 1 and places them into the register 8. And if we go here to the register module, we can see that register 2 and 1 both have the value of 3, and register 8 is initialized with the value of 0. So after this instruction executes, register 8 should have the value of 6. Now, the next instruction utilizes register 8, which in the register module is initialized to 0 and is still 0 when this instruction happens. But with the use of the forwarding unit, the value of 6 in register the newly calculated value of 6 in register will be passed through since it's being used here. So register 8 plus register 11 will be placed into register 2. Register 11 has the value of 4, so 6 plus 4 is 10. After this instruction executes, there will be the branch if equal instructions. The branch if equal instruction. Branch if equal, this instruction will check if register 0 is equal to the register 0, which they're both the same register. So that should be true, and register 0 is initialized to the value of 0. If this condition is true, we'll jump one instruction to this instruction here, which will add the 0th register. So register 0 plus register 10, and register 10 has the value of 10. If this condition is not met or the branch if equal instruction does not work, then register 3 will have the value of register 9 plus register 10. Register 10 has the value of 10 and register 9 has the value of 10. So if this instruction works, does not work, register 3 will have the value of 20. If this branch if equal instruction does work, register 3 will have the value of 10. So now we will comment out the memory file. And we will simulate. And now we'll show the memory list. So after the first period, all the registers are initialized. And after 4 more periods, register 8 should have the value of 6. So 2, 3, 4, 5. Register 8 has the value of 6. Now after one more instruction after one more clock period, register 2 should have the value of 10. or if the forwarding unit does not work, register 2 should have the value of 4. Since register 8 and register 11, since register 8 was initialized to 0 and register 11 has the value of 11. So one more clock period. And we see here register 2 has the value of 10. So now the next instruction will be the branch if equal instruction. So nothing happens. And now we see that register 3 has a value of 10. So that shows that this instruction executed, not this instruction. Because if this instruction is executed, then that means register 3 would have the value of 20, not 10. But register 3 does have the value of 10, as shown in this in the register file. So now this is a concluding the video demonstration of the MIPS 32-bit MIPS processor with 5-stage pipelining. Thank you.